Great. So hi everyone, and so my name is Lionel Garcia, and indeed I'm from the University of Liège, and this is in Belgium in Europe. First of all, thanks a lot for the organization of this workshop. It's really nice to see all your work and these nice presentations. And today I'm really happy to introduce you about prose. So prose, as I said, is a Python package and to build modular image processing pipelines. And image processing pipelines is quite large, so it has been developed for astronomy in particular. So who is prose for? So prose, basically, you will use it for image processing when you get raw images from a telescope or an instrument, and you want to derive from these raw images scientific products. So it totally falls into the data reduction tools when you go to EMAC. But in the past has been used for other things, like commissioning some instruments. It's quite useful to have a tool to manipulate images, to have a feedback from an instrument when you're doing commissioning, or you want to do some specific control. So it has been used for that, especially in the context of the commissioning of an instrument called Spirit on the Speculoos telescope, or to build instrument models. It has also been used, for example, to record and map a bad pixel, for example, on a detector. You can also use prose for data visualization. I will show you a nice example of that later. And actually, for the people doing model fitting, prose can be quite useful. I know sometimes the teams doing model fitting, they rely on external collaborations to get the data, like light curves. We're talking about 1D spectrum or radial profiles, kind of things. But sometimes they want to play with the data as well, and they have to wait for the external collaborator to work on that. So using prose, it gave some teams the freedom to play with the data, to tweak the parameters of the pipelines, and to really be able to get an end on the data. So I think it's quite also useful for the people. And for the rest of you doing, for example, hardcore modeling, I'm sorry, prose is not really useful, but still I have, I think, some nice things to show you. So all prose works. First of all, prose is object-oriented. So it's object-oriented in Python. And we provide to do image processing 3 objects that we call core objects. One of these objects is an image, of course. This is really an image containing data, metadata that you can manipulate. And usually you want to do a range of things on these images. You want to align, you want to calibrate these images. You want to detect sources for sure. Maybe count galaxies, find planet night, why not? And then you want to save your results in some data structures, maybe doing some input-output operations like saving some reduced images, making a video, these kind of things. So in prose, we provide an object called a block. This is a single processing unit acting on an image. And we have a lot of pre-implemented blocks to do a lot of different things. What you will do is you would assemble this block sequentially into a sequence. And that's it. Basically, that's how you would build pipelines with prose. Using this approach, so either inputting one image or several images, is quite convenient, and especially convenient to have each of these blocks developed, tested, and documented individually, independently. So this is really the approach we wanted here to develop with prose, and that's the philosophy. So for example, if you're familiar with Python, here is one example. This is the characterization of the point spread function for one image. As you can see, we start by loading this image as an image object, and then we define the sequence. And here to do that, the sequence is just 5 blocks. First block, we trim the image. Second, we detect some sources. We make the cutouts around each sources. We stack these cutouts into what we call an effective PSF. And then we model this PSF here thanks to a Moffat profile. And that's it. You can apply this sequence to one image, several images. And what's interesting here is that this process is instrument agnostic. So this fits image can load a lot of images from a lot of ground-based telescopes. But if you have specific images, like you have to combine some either fit with different extensions, for example, you can write your own loader, but then the sequence is the same. You can send the sequence to a colleague, it can execute it for another telescope. So that's really the aim, yes. So using this architecture, a lot of people have developed sequences that are much longer than what you saw, like some of 20 blocks, let's say, and ending with different products, scientific products. So people have used prose to study binaries, to study comets, especially to extract the profile for comets, to do spectroscopy on long slit observations, so spectroscopy, People are interested also in using prose to do rotational likers from asteroids. And there is a project, for example, at ESO about satellite pollution monitoring. So a lot of things. Last example I want to show you, this is one of these projects, is the occultation of a star by Iaka. So Iaka is the largest moon of the dwarf planet Haumea. You have a description to the right, a nice image. And you see here a full occultation of Iaka. Prose was used to do this occultation to reduce the images. It consists only of 9-block sequence. And you have full control over the parameters, like if you want to change detection algorithm, if you want to change the stunt trading, if you want to change the way you compute the background, these kind of things. What is nice is that you also have the last block, the 9th block, being a video plot. This is the block that has been used to make this video. You just input a function, taking an image as input, and that's it. You have your video for free, and it's really useful to really monitor what the reduction is doing. So here it's really falling into the data visualization part. So what about exoplanets with the E of EMAC? We did several things with exoplanets. The first project was to obtain a transition spectrum for TRAPPIST-1H. TRAPPIST-1H is the outermost planet of the TRAPPIST-1 system, if you know it. We wanted to show that it was basically the atmosphere was not hydrogen rich. And for that, we developed a pipeline with prose. We copied the pipeline from Kredberg 2014. It was a nice exemplar to show that we could read a pipeline from the literature and just pick the blocks available and working. And for this project, I also thanks a lot Julien David, because it's still a user of prose and is promoting prose in the community, which is really nice. Another example of the use of prose for exoplanets is a lot of test follow-up that is happening with the TRAPPIST telescopes and the Speculoos telescopes. What's nice with prose is that we have some really convenient objects to represent the fluxes, the systematically record everything. And from this object, we can derive some reports. These basically are LaTeX templates. You can generate PDF. So a lot of work about that has been done by Mathilde Timmermans from my team here in Liège. And for example, in the last 6 months, this led to the upload of more than 80 of this report to confirm some planetary candidate by tests. So really a big effort here. Another example, the last one about exoplanets, is this transit search telescope. This is located in Antarctica. It's called ASTEP. And Georgina Transfield was in charge of that. So she developed automatic pipeline for this telescope. Here it was quite an interesting project because we are talking about a really remote location. You have a low bandwidth, so you have to think about what kind of data you want to save, in which form, and as well as the robustness of your pipeline. People are not always there. If something happens with the pipeline, your data is just broken. You cannot check a stack even. So the robustness of pipelines with prose here is really tested, and it improved a lot prose. So what about the motivations? What we wanted when we developed prose? So the first thing is we developed prose because we wanted to translate an IRAF pipeline into Python. And doing that, we wanted to keep something really open source, but most importantly, readable. We wanted the pipeline to be readable from scratch, let's say, and not to have to read thousands of lines of code just to understand what the pipeline was doing. We wanted something really modular because in our team, people are doing other things like rotational liker for asteroids. I mentioned it. We wanted something Python only, dependencies, meaning we could install with pip. We don't have to compile C code to do this kind of things locally. We really wanted something easy to set up. And finally, laptop fast. And this is not just to go fast for the pleasure, but it's really to be able to iterate over sequences, to really be able to switch blocks to see what it is giving on a full observation. And it really helped improving the scientific product at the end of the pipelines that are reposed. So where are we right now in the development? I think we ticked all the boxes I just told you about our motivations. Prose is at the version 2.3.1, but even if the version is 2 and we are going to the 3, it's still a young project. And with the version 3, what we want is really to go from a package developed in a small team to a community development. And for that, we are really relying on people in their own field, trying to develop blocks. So we support these developments. And really, version 3 is about making this a community developed package. But if you're interested in that, you can check out the prose webpage. This is on GitHub, or still on GitHub, the code. You can start the project. Of course, it's always great to have support. And go ahead and check the discussions, because in the next month, we will be really putting a lot of effort in the version 3, and we will really be happy to have you joining that. Thanks a lot. I'm happy to take your questions, ideas, comments, anything.